In this video, we're going to take a look at some vector applications. So situations where we can use our knowledge of position vectors and extend that again to relative vectors to help us solve problems. Situation 1. At 12 p.m. on a Monday, a ship has position vector -180, -130 kilometers from a port and is moving with velocity vector -8, -6 kilometers per hour. So if we wanted to describe exactly how we keep track of the position of this ship, I'm going to call it ship A, we can define its position over time. So this is where time becomes very important, and I use a T to represent time. So if we think about this ship A, I'm going to call R as my displacement. The displacement of A is going to be its initial displacement, or its initial position from the port, which the port is our origin, plus how many hours it moves with its current velocity. So if we wanted to form a vector to show how the position of A is changing from the port, it would be 180 -130 plus t times its velocity. And this is a really important part of forming these position vectors to show displacement. What we actually want to find out in this first question is where is the ship at 5 p.m. on that same day, so exactly 5 hours later. So when t is 5. Well, this is very easy knowing that we've just set up this displacement vector. So ship A is going to be 180 -130 plus 5 lots of its velocity vector. And we can work that out to 140 -160. So we could say at 5 p.m. the ship will be at position 140 -160 kilometers from that port. Now that we've got that displacement from that origin or that port, we can determine the distance the ship is from the port at 5 p.m. So this is where we want to find the magnitude. And we can simply do that because we've got a position vector with I and j components. We can use Pythagoras because we've got that right angle triangle. And we can work out that it's 212.6 kilometers from the port at 5 p.m. We can extend this by actually finding out some times if we know the distance it is from the port, so doing it in reverse. So let's go back to our initial vector that we had describing its movement. We had 180 -130 plus t lots of -8, -6. I can actually simplify this a little further by putting my I components together and then my j components. So I can describe my I component as 180 take 8t, and then I could define my j components as -130 take 6t. That makes it a lot easier to write a vector for the displacement of this ship A. So when it's 220 kilometers from the port, obviously 220 squared would be the same as the I component squared plus the j component squared. And then we can simply pop this into solve in main on our class pad. And we get a solution that time is 0.72 or time is 12.48, knowing that obviously we're dealing with quadratic here. So this is a good opportunity to pause the video and just check that you can recreate these solutions in your ClassPad. Now hopefully you've verified that the time is 0.72 hours or 12.48 hours, depending on the ship's movement. So we actually have to work out the time. So here we can see that we've only done not even 1 hour of travel. So this would be from 12 p.m. We've got to work out 0.72 of an hour, and 0.72 of 60 minutes is just over 43 minutes. So we could say that it's 220 kilometres at 12:43 p.m. So we want to get to the nearest minute. And then we can also find out it also is going to be 12 hours later. So it's going to be over 12 a.m. and 0.48 is going to be almost half an hour. So it's also going to be at 12:29 a.m. on the Tuesday morning. So now I'd like you to pause the video and work out at what time that this ship is 300 kilometres from the port. Okay, so taking that same idea that we're going to find the magnitude of by squaring the I and j components and equaling them to 300 kilometres. Using solve mode, we get t is negative 14.63 and t is 27.83. So we know that time has to obviously be bigger than 0, so we only have one solution of 27.83, and our time here is in hours. So if we think that it's over 24 hours later, so if we left port at 12 p.m. on the Monday, we're going to be at 24 hours at 12 p.m. on the Tuesday. We've got a 3 extra hours there, so it's definitely going to be 3 something p.m. and that will be on the Tuesday. Working out 0.83 of an hour will get us to the nearest minute at 3:50 p.m. on the Tuesday. In our second example, we're going to have a look at finding at what time and at what position two objects or two ships collide. So if they've got their initial position and they're moving with a particular velocity, when two things collide, it means that they're actually going to meet at that same point. So we can find a position vector for that. It also means that the position of, say, tanker A and the position of tanker B when they collide will in fact be equal. So what we want to do in this case to find if they collide is to find out that can we equate their positions to be equivalent. Let's first define how the movement of tanker A is going to go. So the displacement of A is going to be its initial vector of 186.44, and we're going to add onto that its velocity, and let's use time t in hours. Every hour it's going to move 8i plus 12j. Let's actually put our I and j components together because it makes it for more efficient calculations. So it's 186 plus 8t in the I component and 44 plus 12t in the j component. Looking at the movement that's going to happen, so the position representing now tanker B, we've got 228 plus 58 as its initial position, and it's moving with negative 16i plus 4j. So let's try and write that in terms of I and j straight away. So looking at the I values, we'll have 228 take 16 times the amount of time that velocity vector, and we'll have 58 plus 4tj. So these obviously are our velocities are multiplied by time. So what we want to find out now is this position where they're going to collide, which means the I component and the j component for those are going to be equivalent. So let's take the I components first. So we've got 186 plus 8t should be equivalent to 228 take 16t. Simplifying this, and solving for t, we should find t as 1.75 hours. That's the I component. What we do want to make sure is the j component is also exactly the same, because we don't want a to be obviously the same I component but a different j component, because then they won't collide. So if we have a look at our j components now, we've got 44 plus 12t should be equivalent to 58 plus 4t. So we've got 8t equals 14 and t is 1.75 hours. Now, because we have the I and j components both giving us the same t value for time, A and B will collide. So what we need to do now is find the position vector and the time this will happen. So therefore, the position that this is going to happen, we can simply just take one of the vectors. So I'm going to take the vector here for tanker B. So if I substitute that in, we're going to get 228 take 16 lots of 1.75 and 58 plus 4 lots of 1.75, and that's going to give me 265 for my I and j components. So in summary, we can say A and B will collide at 1.75 hours after they take off, which is 7 a.m. So that will be 8:45 a.m. at the position of 200I plus 65 j kilometres. So now it's your turn. I'd like you to have a go at the following two questions. The first question takes the idea where we need to find the positions of ships at certain times after they've been moving, the distance between ships. And our second question is to determine whether or not two ships collide. So I'd like you to pause the video and have a go at those two questions and come back and check your solutions. Please, in question 1, really take note of the hint, taking into consideration that we know about relative vectors. So using A relative to B, meaning what's the vector of A from B, and that will very quickly find our distance. Solutions for question 1. The position of A is 25.5 kilometres and B is 4:27 kilometres at 10 a.m. The distance between them, well, if we look at the distance of A from B, that's a really quick way of finding that vector of 21, negative 22. So we can find the magnitude of this of 30.41 kilometres. Going back to A relative to B and what that would look like using the standard vectors with their position and velocity, we can form a really nice relative vector. We can then make this equal to 30 kilometres, and we find that this happens at 9:56 a.m, which makes a lot of sense. In question 2, if two ships are going to collide, then we can put their I and j components equivalent, and checking that they come out with the same time, that after 5 hours that they will both collide. We can substitute t as 5 back into one of the displacement vectors and find that A and B will collide at 10 a.m. with position 2243 kilometres.